Now student, we are going to discuss this question number 2.17. In this question it is given to you 1 mole of an ideal gas at standard temperature and pressure occupy 22.4 liter. Clear? So I can see in this question it is given to you molar volume. Clear? Molar volume, and this is equal to 22.4 liter. Clear? 22.4 liter. We can write like this: 22.4 multiply 10 to the power minus 3 meter cube. Clear? So this is molar volume. Now it is given here what is the ratio of molar volume to atomic volume of 1 mole of hydrogen. Clear? So let's suppose according to question we can say, let's suppose radius of a hydrogen atom. Clear? Radius of hydrogen atom is given to you, this is 1 angstrom, and 1 angstrom means we can say 10 to the power minus 10 meter. Clear? Clear? So I can say what is volume of hydrogen atom. Clear? So volume of hydrogen atom, this is given by 4 by 3 pi r cube. Clear? So what is volume of 1 mole of hydrogen atom? Clear? So we can write like this: volume of 1 mole of hydrogen atom. Now we know this is volume of 1 atom of hydrogen. Clear? This is volume of hydrogen atom, or we can say, and volume of 1 mole of hydrogen atom. Clear? So 1 mole of hydrogen, or we can say this is atomic volume. So it is given by Na multiply 4 by 3 pi r cube. Clear? Now what is Na? Na is equal to what? This is Avogadro number. So we can write like this: 6.023 into 10 to the power 23 multiply, this is 4 by 3, 3.14, and radius of hydrogen atom is given to you 10 to the power minus 10. So 10 to the power minus 10 whole cube. Clear? So from here we can say approximately, I am saying this one is approximately cancelled out. Clear? So this is equal to 1. So we can say 6 multiply 4. Clear? So near about we are getting this is 24 into 10 to the power 23 multiply 10 to the power minus 30. Clear? So I can say volume of 1 mole of hydrogen atom, this is given by 24 into 10 to the power minus 7, this is meter cube. Clear? So I can say this is near about. Clear? We can see this is actually atomic volume. Clear? So atomic volume is given by 24 into 10 to the power minus 7 meter cube. Now in this question it is given molar volume 22.4 into 10 to the power minus 3 meter cube. Clear? Now our objective here is to find the ratio of molar volume to atomic volume. So I can write like this: this is molar volume to this is atomic volume. Clear? And this is equal to what? 22.4 liter means this one. Clear? And 24 multiply 10 to the power minus 7. Clear? So near about, you can say near about this one is cancelled out. Clear? And you will find approximately answer 0.999 something. Clear? And approximately if we find molar volume is 10 to the power 4 times of atomic volume. Now we have to find here why this ratio is so large. Clear? Actually we know atomic volume is related to volume of all hydrogen atom. Clear? But if we are talking about molar volume, in molar volume actually the interatomic spacing between two atoms, that is very large compared to size of an atom. That's why we can say that we are getting molar volume, this is 10 to the power 4 times of atomic volume. Clear? So this is all about this question. Clear to everyone? Now dear student, we are going to discuss question number 2.18. Clear? In this question it is given to you, explain this common observation clearly. If you look out of the window of a fast moving train, clear, the nearby tree, houses, etc. seem to move rapidly in a direction opposite to the train motion. Actually this is just a common observation. Clear? Whenever we are traveling from one place to another place via train, at that time we always experience, let's suppose if we are sitting nearby a window, we always experience that tree or the person or the child, whatever standing outside, that is going in an opposite direction of our direction of motion. Why this is happening? And let's suppose at the same time if we are observing hills, if we are observing a very distinct object, we find that they appear to be stationary. Why this is happening? Because there is a word that you always you should know here, that is known as line of, this is known as line of sight. Clear? There is a word, this is line of sight. Line of sight is what? Actually we can see the line joining eye and an object is known as line of sight. Clear? So now if I talk about a nearby object, the line of sight, or we can say this line of sight changes very rapidly. Clear? Let's suppose this object is very near to me. When I am going in this direction, at the same time I am observing that object, and I am my line of sight is actually moving like this. Clear? It means what I am saying, for the nearby object, line of sight changes very fastly. Clear? But what will happen with distinct object? For distinct object, you can see if you are observing a let's suppose a mountain, so we can say actually distance of that object from this eye is very large, or we can say this line of sight is very large, or we can say whenever we are moving in a particular direction, the change in line of sight that is taking place is very small. So that we can see that object that is placed at a very large distance from us, it appears to be stationary. Clear? It appears to be stationary, but what about nearby object? Because line of sight is changing very rapidly, so that's why all the object, all the person, that all the poles, tree, whatever they is standing outside of the train, it appears to move in an opposite direction of the direction of motion of a train. Clear? So this is all about this question. Clear? Now dear student, we are going to discuss here question number 2.19. Clear? In this question, initially some information is given to you about parallax. Clear? And after that a question is asked to you. Clear? So now let us try to understand this question. Initially it is given the principle of parallax is used in the determination of distance of very distinct stars. Clear? Actually we used a parallax method. Actually this is an indirect method to measure the distance between two stars. Clear? Or we can say, let's suppose if we want to find distance of a star from our position, at the time we can utilize here parallax method, but this is indirect method. Clear? So now it is given here some information, initially some information is given, and that is not required for this question. Actually the thing that is required in this question from here only. Clear? Otherwise all are the information you can read here. Clear? So the baseline AB of the line joining the earth to locations 6 months apart in its orbit around the sun. Clear? So this is the baseline is about the diameter of earth orbit. This is 3 into 10 to the power 11 meter. However, even the nearest stars are so distinct that with a long baseline they show parallax only of the order of 1 second of arc or so on. Clear? Now a parsec is a convenient unit of length on astronomical scale, and it is the distance of an object that will show a parallax of 1 second from opposite end of a baseline equal to the distance from earth to the sun. How much is the parsec in terms of meter? Now first let us try to understand this question very easily. Clear? Let's suppose we can say this is our position. Clear? Let's suppose we are saying this is our position. Clear? And let's suppose I can say this is earth. Clear? Let's suppose this is sun. Clear? So actually we are taking this distance as 1 parsec. Clear? 1 parsec, and we are taking here let's suppose an arc is formed here, and this angle is what? This is 1 second. Clear? This angle is what? 1 second. And this arc length, this is equal to distance between earth and sun. Clear? And we can say this is equal to 1 astronomical unit, and this is equal to 1.496 into 10 to the power 11 meter. Now what is our objective? Our objective here is to calculate 1 parsec. Clear? So how can we calculate? Directly we can apply here angle. Angle equal to what? This is arc upon radius. Clear? actually you can see if you are observing from here, it means radius is equal to what? Radius is equal to 1 parsec. So I can say 1 parsec, and this is given by arc upon angle. Clear? Arc is given to you 1 astronomical unit, 1 astronomical unit, and what about angle? Angle is given to you 1 second. Clear? So now here first I am writing here astronomical unit in terms of meter, as well as I can also convert here this angle in second into radian. Clear? This is compulsory condition. So from here we can see 1 astronomical unit, we can say this is 1.496 into 10 to the power, we can say this is 11. Clear? Divided by 1 second. First we convert this 1 second into minute, I can say this is 1 by 60. Then we can convert this into degree. Clear? So I can say 1 by 60 into 60. Now how can we convert degree into radian? This is pi by 180. Clear? So from here if you solve it, you will find here 1.496 into 10 to the power 11 divided by 4.95. Clear? This value I am directly writing of the denominator 4.85. This is 4.85 into 10 to the power minus 6. Clear to you? 4.85 into 10 to the power minus 6. So from here you can say near about, we can say this is equal to 3. Clear? So we can write like this, 1 parsec. 1 parsec, this is equal to 3.08 into 10 to the power 70. Yes or no? 1 parsec I can see this is 16. Yes. 1 parsec we can say this is 3.08 into 10 to the power 16, and this is meter. Clear? So here we write value of parsec in terms of meter. So this is important result. You can directly memorize this value also, that 1 parsec equal to what? 3.08 into 10 to the power 16 meter. Clear? And we can say actually this is a very large distance. Clear? That's why we can say this is used to measure distance of distinct star. Clear? And this value is again important, 1 astronomical unit. 1 astronomical unit is what? This is distance between sun and earth, and this is given by 1.496 into 10 to the power 11 meter. Clear? So then how can we define 1 parsec? 1 parsec is a distance by which an arc that is subtending an angle of 1 second only, and this distance, this arc length is equal to 1 astronomical unit. Clear? So this is all about this question. Clear? Now dear student, we are going to discuss this question number 2.20, and in this question it is given to you the nearest star to our solar system is 4.29 light years away. Clear? So nearest star is located at a distance of 4.29 light years. How much is this distance in terms of parsec? Okay, fine. So first, you know here very well that total distance, if we are talking about distance of star, clear? Distance of star, it is given to you 4.29 light years. So 4.29 light years. Now you know 1 light year equal to how many meters? Clear? So we can write like this, 4.29 into 9.46 into 10 to the power 15 meter. Clear? 1 light year, this is equal to what? 9.46 into 10 to the power 15 meter. Clear? Now actually we know 1 parsec. Clear? 1 parsec is equal to what? 1 parsec is equal to, we can say 3.08 into 10 to the power 16 meter. Clear? 10 to the power 16 meter. So actually we have to find this distance of a star in terms of parsec. Clear? So we can actually write like this, distance of star divided by, I can say this is 1 parsec. 1 parsec, this is equal to what? This is equal to 4.29 into 9.46 into 10 to the power 15. It is divided by 3.08 into 10 to the power 16. You can say from here this one and this one cancelled out, only 10 remaining. Clear? So now we can say near about this one is cancelled out. Clear? This is 9.5, this is 10. Definitely this will come out to be 1 point something. Clear? And 1 point something multiply this one. Clear? So if you find here, you will find this is equal to we can say this is 1.32. Clear? If you actually calculate here, you will find this ratio 1.32. Clear? So at that time we can write like this: distance of star, this is equal to 1.32 parsec. Clear? So like this we can write here this value of distance of star in terms of parsec, and this is equal to 1.32 parsec. Clear? Now next part is here, how much parallax would this star that is actually known as Alpha Centauri show when viewed from two locations of Earth 6 months apart. Clear? Now listen carefully. Actually the Earth revolves around the Sun. Clear? And the total time period is 1 year. Clear? And we can say in 6 months the total distance covered by Earth, this is equal to half of circumference. Yes or no? So from here we can write like this, just a minute, we can write like this: distance covered, or in terms of, you can say this is arc length. Clear? So this is equal to what? We can say this is equal to 1/2 into circumference, this is 2 pi r. Clear? So from here we can say this is pi r. Now r is what? R is, we can say in this case, Earth is revolving around Sun. Yes or no? So actually we can say r is a distance between Earth and Sun, and that is equal to astronomical unit. Clear? So we can say this is equal to pi and multiply 1 astronomical unit. Clear? Now what is our objective? Our objective here is to calculate parallax. Parallax means we have to find here angle. Clear? So we can write like this: angle subtended Yes. Now our objective here is to find angle subtended. Clear? So angle subtended, this is equal to what? Yes. So from here we can say angle subtend. So angle, this angle you will find in seconds. Clear? Because here we are having distance, this arc length is in astronomical unit. Clear? And this is multiplied with pi. Clear? It is given pi multiply 1 astronomical unit divided by 1.32 parsec. Clear? So from here we can write like this: 1 astronomical unit. So 3.14 multiply 1 astronomical unit. This is equal to what? 1.496 into 10 to the power 11 divided by, this is equal to, or you can directly say, actually you can directly say here, because you are taking here this distance in astronomical unit and this distance is what? Parsec. So you will find this angle in second. So directly you can say pi 3.14 astronomical unit divided by 1.32 parsec. Clear? So now if you calculate it, you will find this angle is near about 2.38. Clear? You can say this is one, if you divide it, so 2.38 and in second. Clear? So this is what? This is parallax, or we can say this is angle subtended by an arc. Clear? On a particular location. Clear? So correct answer we have 2.38 second. Clear to everyone? Now dear student, we are going to discuss question number 2.21, and in this question it is given to you: precise measurement of physical quantities are a need of a science. Clear? Definitely we need a precision measurement, because sometimes the situation is just like this: if we do not have any precision measuring data, at the time it may lead to some dangerous situation also. Clear? So precise measurement of a physical quantity are a need of science. Clear? Fine. For example, to ascertain the speed of an aircraft, one must have an accurate method to find its position at closely separated instant of time. Exactly. Clear? This was the actual motivation behind the discovery of radar in World War II. Clear? Think of different example in modern science. Okay. So if we talk about modern science, let's suppose if we talk about one instrument, that is electron microscope. Electron microscope. Actually this electron microscope utilize an electron beam. Electron beam of near about 0.2 angstrom to find length, or we can say to find length or size of very small particles, like if I take here example, virus, bacteria and so on, etc. Clear? So actually if you find here, if we want to find the measure the size of a bacteria or a virus, at that time we need an instrument, and that instrument should give precise result. So we utilize here electron microscope. Electron microscope utilize here an electron beam of 0.2 angstrom, and it finds length or the size of a very small particles on an object like virus, bacteria and so on. Clear? And actually you can see the main motivation behind this precision measurement is the World War II, because we want to find the exact situation of an aircraft, because and due to which we can see there is an origin of radar is to be take place. Clear? So one example already given here in this question, and here we also proposes one example. This is related to modern science. Clear? So this is all about this question. Clear? Now student, we are going to discuss this question number 2.22. Clear? In this question it is given to you, just as precise measurement are necessary in science, it is equally important to be able to make rough estimate of a quantity using rudimentary ideas and common observation. Yes, actually my dear students, we are actually moving towards a precise measurement. Clear? And definitely this is a very good approach to solve any problem, but sometimes it is very difficult to find accurate data. Clear? And at the time we have to find some rough estimation, and that rough estimation we can find by taking some observation from surrounding. Clear? So now this question is based on some this question is based on that idea. Now we have to think of by which we can estimate the following estimate that is very difficult to obtain. Clear? So now you can see here some situations are given to you, A, B, C and D and E, and now we have to find, can we find here that rough estimation of the quantity that we need to measure? Yes. So now first we are going to discuss part number A. Concentrate on a screen. So now we can see this is part number A. Clear? This is part number A. The total mass of a rain bearing clouds over India during monsoon. Now listen carefully. On an average, if I talk about rainfall in India, average rainfall, it is assumed, average rainfall in India, it is assumed to having a height of 1 meter. Clear? It is having height of 1 meter. Average rainfall in India 1 meter, or we can say this is equal to 100 centimeter. Clear? Now if we talk about total surface area of India, total surface area of India. Clear? So total surface area of India we have 3.3 into 10 to the power 6 kilometer. Clear? This is what, this is total surface area of India. We can convert into meter also, 3.3 into 10 to the power 12 meter. Clear? Or 9 meter. Clear? This is equal to 10 to the power 9 meter. Clear? This one. Now can we find here total volume? Yes. So we can calculate here total volume. Total volume is given by, we can say this height as well as multiplied with area. So area multiply height, this is equal to 3.3 into 10 to the power 9 multiply 1. Clear? So from here we can say this is equal to 3.3 into 10 to the power 9 meter cube. This is volume of rainfall in India. Clear? Now what is our objective? We have to calculate here total mass. So total mass is given by what? Total mass, we can say this is equal to density multiply volume. Now density of water, this is equal to what? 10 to the power 3. Yes or no? 1000 kilogram per meter cube, and it is multiplied with 3.3 into 10 to the power 9. So from here we can say this is 3.3 into 10 to the power 12. Yes or no? So 3.3 into 10 to the power 12 kilogram. Clear? So we can say like this, we can find a rough estimation of total mass of rain bearing clouds over India during monsoon. Clear? So this is all about part number A. Clear to everyone? Yes. Now we can find here how can we calculate mass of an elephant. Actually we can take a very funny incident. Let's suppose we have a boat, and boat is having a base area that is equal to capital A. Clear? Now let's suppose at this time boat is empty, there is no elephant inside that boat. Now you can say, sir, when elephant will put a leg on the boat, definitely the boat will sink. Clear? So let's suppose we are assuming no, boat is just floating. So initial condition, listen very carefully what I am saying to you. I am saying here base area of boat is A. Clear? I can see depth of boat in water when there is no elephant in the boat. At that time we can say, let's suppose that is x1. Whenever we place an elephant on a boat, at the time let's suppose total depth now changes to x2. Clear? So can we find first how can we find here mass of an elephant? So when this boat is actually floating, in this condition we can see, listen very carefully, in this condition we can utilize actually Archimedes principle, and Archimedes principle says weight of elephant, this should be equal to weight of liquid displaced, Clear? So from here we can write like this, weight means this is equal to mg, and this should be equal to density of water. Clear? Volume of liquid displaced and multiplied with g. I can say g and g is cancelled out. So from here can we calculate mass of an elephant? Yes. What about density? Density of water we have, that is 10 to the power 3, and volume we can write like this, A x2 minus x1, because here we will take volume of the water that is displaced by element. Clear? So if we know here density, if we know the surface area of, or we can say base area of a boat, and if we know x2 minus x1, at that time you can easily calculate that what is the mass of an elephant. Clear to everyone? So actually this is just a rudimentary concept, or you can say here you are applying Archimedes principle, and by using Archimedes principle you are calculating mass of a weight. Clear? Now you can say, sir, what about mass of a boat? So actually whenever initially we are taking boat is empty, at the time the boat is actually sink by x1 amount due to its self weight, and that actually that weight is a constant in both the situation. Clear? So additional depth, that is additional depth of this boat, it is occurred due to mass of an elephant. Clear? So we can say like this, we can calculate this mass. Clear? Now listen very carefully. Now if we talk about wind speed during a storm. Clear? Now concentrate here. Let's suppose I am taking, this is ground. Clear? Let's suppose this is ground. Let's suppose we have an air filled balloon. Let's suppose this is balloon. Clear? This is balloon, and at this time I am assuming there is no wind that is blowing. Clear? And let's suppose height of this balloon, that is h from this surface. Clear? Now let's suppose after some time when I place this balloon in a air or in a wind, at the time let's suppose this is position of a balloon, and let's suppose it is making an angle theta, and let's suppose at the time this distance covered is x. Clear? So can we find here value of tan theta? Yes. Tan theta, this is given by x by h. So from here we can calculate x equal to h tan of theta. Clear to everyone? Now let's suppose from this position A to position B, total time taken by this balloon is small t. So we can write here velocity, or we can write like this, this is wind velocity. Clear? So wind velocity, this is given by distance covered over time. Clear? Distance covered equal to what? This is equal to h tan theta and total time t. Now you say, sir, h we know already, theta we can measure, and time t we can measure by we can say stopwatch. Clear? So like this you can calculate here wind velocity. Clear to everyone? Yes. Now Now let's suppose we want to find that what is the total number of strands of hair on your head. Clear? So let's suppose I want to know the total number of strands on my head. Clear? So how can I find? So for that one I can assume here, let's suppose first I am counting total number of strands in 1 centimeter square area. Clear? And let's suppose if I know total area of my head, at the time I can directly multiply. Yes, and we can calculate here total number of strands. Clear? Yes. Now if we talk about part number E. In part number E it is given the number of air molecules in your classroom. Clear? So let's suppose we are assuming a size of classroom, or we can say volume classroom. Clear? So let's suppose I am taking 8 into 6 into 4 meter. Clear? So from here you can say this is 24, 8. So we can say 24 multiply 8, and this is equal to 192 meter square. So this is total volume of a classroom. Clear? Now if I talk about 1 mole of gas. Clear? So 1 mole of gas, it actually contains 22.4 liter. Clear? Or we can say this is equal to 22.4 into 10 to the power minus 3 meter cube. Clear? This is total volume. Clear? So can I say here 22.4 into 10 to the power minus 3 volume if we have, then total number of air molecule is equal to Avogadro number. So this is equal to 6.023 into 10 to the power 23. Clear? Now let's suppose if I am saying total volume we have 192, this is the volume of a classroom. Can we calculate here total number of air molecules present in classroom? Yes, we can write like this: 6.02 into 10 to the power 23 divided by 22.4 into 10 to the power minus 3 multiply 192. Clear? So from here we can say this is near about 3. Clear? And it is multiplied with this one. Clear? So if you say 20 multiply 8, that is equal to 160, 180, and this is near about what? We can actually calculate. If you calculate here, you will find here this is equal to 51.6 into 10 to the power 26 molecules. Clear? So we can say near about 10 to the power 28 molecules, 10 to the power 28 air molecules we have in our classroom. Clear? So actually you can directly see 192 divided by 22.5 4, and this is 6.02. If you calculate it, let's suppose near about 4. Clear? And we can say this is near about 50. Clear? So you can say the exact answer you will find 51.6 into 10 to the power 26, and near about total 10 to the power 28 air molecules is present in a classroom. Clear to everyone? So this is all about this question. Now dear student, we are going to discuss this question number 2.23, and in this question it is given to you: the sun is a hot plasma with its inner core at temperature exceeding 10 to the power 7 Kelvin, fine, and its outer surface at a temperature of about 6000 Kelvin. Clear? At this high temperature, no substance remain in a solid or in a liquid phase. Clear? In what range we expect the mass density of sun to be? Clear? So our objective in this question is to calculate mass density of sun. Clear? So we can write like this: mass density of sun. Clear? Mass density of sun, this is equal to, I can say this is mass of sun divided by volume of sun. Clear? Now mass of sun, it is given to you in this question. This is 2 into 10 to the power 30 divided by what is volume of sun? Volume of sun, we can say this is 4 by 3 pi r cube. Clear? So from here we can say this is 2 into 10 to the power 30 divided by 4 by 3 pi. We can say this is 22 by 7 multiply what is value of r? R means radius of sun is given 7 into 10 to the power 8. So 7 into 7 into 7 into 10 to the power 24. Clear? So from here we can write like this: mass density of sun, or we can say we can represent it by rho. Clear? So mass density, this is given by 2 into 10 to the power 30. So directly you can say this is 2 into 10 to the power, clear? This is 10 to the power 30 and this is 10 to the power 24, means this is 10 to the power 6, clear? From here you can also write like this is 4 by 3 multiply 22 multiply, I can say this 7 and 7 is cancelled out and this is 7 into 7, clear? From here you can say this is what 2, clear? So this is 3 into 10 to the power 6 divided by, clear? We can see this is 44 into 49, clear to everyone? So from here we can write like this, if we solve it you can say let's suppose I am writing this is 3000 into 10 to the power 3 divided by 44 into 49, clear? So I am taking it nearby 50, so nearby 50 if I am taking, this is to be near about we can say 60, clear? This is near about 60, clear to everyone? Yes. Now you can say here we have this is 60 and this is 44, so we can say this is 30 divided by 22 into 10 to the power 3, or we can say this is 15 divided by 11 into 10 to the power 3 kilogram per meter cube, clear to everyone? So we can say 15 by 11 is equal to what? We can say rho it is equal to 1 point. Now here we have 4 left, so approximately I can say 1.4 into 10 to the power 3 kilogram per meter cube. So this is what? This is mass density of sun, clear to everyone? This is mass density of sun. Now you can say this mass density actually lies in a range of between the solid and liquid, clear? The density of gas, it will never lies on this range, clear? It means now you can say, sir, in the inner core of a sun we have a temperature of 10 to the power 7 Kelvin and at the outer surface we have temperature 6000 Kelvin, clear? So whenever we have this much amount of temperature, how can we can say this density lies between the range of solid and the liquid? So actually if we talk about gravitation attraction that is exerted by inner layer of a sun on the outer surface, that is very large, clear? So we can say actually the mass density of sun is very large, or we can say it lies between solid and liquid, clear? So this is all about this question, clear to everyone? Now dear student, we are going to discuss this question number 2.24, clear? In this question it is given to you, when the planet Jupiter is at a distance of 824.7 million kilometer from Earth, clear? So we can say it is given when the planet Jupiter is at a distance of, clear? So let's suppose this is Jupiter and let's suppose here we have Earth, clear? Now it is given in this question that this planet Jupiter is at an angle of 824.7 million kilometer. So let's suppose I am saying this distance is 824.7 million kilometer, clear? Clear to you? Yes. Or you can also write like this, just a minute. You can also write like this, this is actually distance, clear? And this distance is equal to r, this is equal to 824.7 into 10 to the power 6 kilometer, clear? Now it is kilometer from Earth, its angular diameter is measured to be, means we can see if we talk about this angle theta, clear? So this angle theta is given to you 35.2 to 35.72 second of arc. Calculate the diameter of Jupiter. So again a very simple question. Here we can apply one formula, angle is given by this is arc upon radius, clear? So from here what is our objective? Our objective is to calculate this diameter, clear? And this diameter we can see actually this is arc, clear? So from here we can see arc, this is given by angle multiply radius, clear? So now we can write like this, this arc means we can say this is diameter of Jupiter and this is given by angle is given to you 35.72 second, clear? So first we convert this angle into degree. How can we convert? So first if we divide with 60 into 60, it is converted into degree, clear, and if we multiply it with pi by 180, now it is converted into radian, clear. So this is angle, but what about radius? Radius is given to you 824.7 into 10 to the power 6 kilometer, clear. So now from here you can see we actually utilize this calculation most of time, that pi divided by 60 into 60 into 180, clear, and this is equal to, this will come out to be 4.85 into 10 to the power minus 6, clear, and multiply 824.7 into 10 to the power 6, and this distance you will find in kilometer, clear. So from here we can say this one and this one cancelled out, clear. So from here approximate, if we find here approximate calculation you can see we can write like this, this is near about 36 into 5, clear, into 824.7, and this is in kilometer, clear. So 36 multiply 5, we can say this is what 30, we have 3, so this is 180, so 180 multiply 825 kilometer, clear. So from here we can see if you multiply 18 with 825, we can see this is 10, we have 90, we have 2, so 36 9, this is 45, we have 4, 18 8, 18 multiply 8, so 18 multiply 8 we can see this is 144, 144 and 4, this is 148 kilometer, clear. So from here we can also write like this, this is equal to 1.48 into 10 to the power 5 kilometer, clear. So this is what, this is diameter of Jupiter, clear. So this is all about this question, clear to everyone. Now student, we are going to discuss this question, question number 2.25, clear, and in this question it is given to you, a man walking in briskly in rain with speed v must slant his umbrella forward making an angle theta with vertical, clear. So actually what is this given situation, let's suppose this is ground, clear, and let's suppose this is person, clear, and let's suppose this person is having an umbrella in his hand like this, clear, and it is making an angle theta with vertical, clear, this umbrella is making an angle theta with vertical. Now this person is going in this direction with velocity v, it is given in a question, fine. As student derives the following relation between theta and v, and it is given in this question v equal to tan theta, as student derived this relation, clear. Now we have to check that this relation has a correct limit. Now listen carefully, if we talk about left hand side and right hand side, in left hand side we have dimensional formula m0 L1 t minus 1, clear, m0 L1 t minus 1, and what about dimensional formula of tan theta, because this is trigonometry ratio, and in trigonometry ratio we can say this is m0 L0 t0, clear. It means we can say left hand side and right hand side dimensions are not same, or we can say dimensional formula is not same. It means the student derived this relation tan theta equal to v, this is wrong, clear. So now we are assuming that there is no strong wind and that the rain falls vertically for a stationary man, okay fine. Do you think this relation can be correct? No, this relation is not correct, number one thing. Second, if this relation is not correct, can we correct this relation? Yes. How can we correct it? If we write this tan theta is equal to v by u, if we write this tan theta equal to v by u, at the time you will find in numerator and the denominator, what I am saying to you, listen very carefully, tan theta equal to v by u. So in numerator and denominator we are having unit of meter per second, and dimensional formula is m0 L0 t0, and at the time you can say left hand side and right hand side is same, and this is correct formula, clear. You can also understand this situation like this, you can see this person is going in this direction, clear, in this direction, clear, and rain, actually rain is coming in vertically downward direction with velocity u, clear. So here we will find relative velocity, clear. So for relative velocity, how can we write here? We can write like this, we can write like this, let's suppose this is v, this is what u, and this is resultant velocity, clear, and definitely this rain is making an angle theta with this person, clear. So definitely this person will open this umbrella in just opposite direction like this, clear, at an angle theta with vertical, clear. So from here you can say tan theta. Tan theta is equal to what? I can say tan theta is given by V by U. Clear to you? So correct relation is this one, but student write this relation and this relation is absolutely wrong. Clear? So this is all about this question. Now student, we are going to discuss this question, and this question is 2.26, and in this question it is given to you. It is claimed that 2 cesium clock, if allowed to run for 100 years free from any disturbance, it may differ by only 0.02 second, clear. So we can write like this: total difference in time period that we are getting 0.02 second, clear. It is clear. Now it is also given the total time is given to you 100 years, clear. So can we convert this time into seconds? Yes. How can we write 100 in 1 year? Let's suppose total 365 days. In 1 day we have total 60 into 60 seconds. Clear to you? So like this we can find this time in second, clear. So if we write here fractional change in time delta t by t, this should be equal to what? This is 0.02 divided by 100 multiply 365 multiply 60 into 60. Clear to you? So from here we can say this is fraction change in time period 0.02 divided by 100 into 365 into 60 into 60. Clear? So if you solve it, you will find this answer will be near about this one, clear. This is the fractional change. So from here we can say actually we will find here accuracy. So we can say here we are getting accuracy of 10 to the power minus 11 in 1 second, clear, because we are talking about in 1 second. So we are getting 10 to the power minus 11 in 1 second, or we can also say that we have accuracy of 1 in 10 to the power 11 second. Clear to you? So accuracy of 1 in 10 to the power 11 second, clear. So this is all about this question. Now student, we are going to discuss this question number 2.27, and in this question it is given to you, estimate the average mass density of a sodium atom assuming its size to be about 2.5 angstrom, clear. So in this question it is given to you, radius of sodium atom is 2.5 angstrom, or we can say this is equal to 2.5 into 10 to the power minus 10 meter, clear. Radius is given 2.5 angstrom and 2.5 into 10 to the power minus 10 meter, fine. Now use the known values of Avogadro number and atomic mass of sodium, okay, fine. So now we have to find first the mass density of a sodium in its crystalline phase. This is given to you, and we have to find the mass density of sodium atom, clear. So how can we find? We can find mass density of sodium atom. We can say this is equal to mass of atom divided by, clear, divided by, we can say that is volume of sodium atom, clear. So mass of atom, how can we calculate mass of atom? Directly we can say here, for the sodium, what is molar mass? This is 23 gram, clear, and divided by Avogadro number. At that time you can find the mass of sodium atom, clear. So Avogadro number means 6.023 into 10 to the power 23, clear. So mass of sodium atom, this is given by 23 divided by 6.023 into 10 to the power minus 23 kilogram, clear. Clear to everyone? It is given here, this is 10 to the power 23. Just a minute. It is multiply 10 to the power minus 23. Clear to you? So from here we can see mass of sodium atom, this is given by, this is near about 4 or little bit 4, so 3.8 into 10 to the power minus 23 kilogram, clear. This is kilogram. So I can say mass of sodium atom, this is given by this one, clear. Now we can write this value here, 3.8 into 10 to the power minus 23 divided by, what is volume of sodium atom, Clear? Volume of sodium atom, this is given by 4 by 3 pi r cube. R is given to you, this one. So can we write like this? This is 5 by 2 multiply 5 by 2 multiply 5 by 2. Clear? And it is multiplied 10 to the power minus 30. Clear to everyone? So from here you can calculate density of sodium atom. Clear? So density of sodium atom, this is given by, now we can say this is 10 to the power 7. Clear? So this is near about 4. Clear? So we can write like this, this is 3 divided by pi into 5 into 2. Clear? Into 2 into 2 multiply 5 into 5. Clear? And we can say this is 10 to the power 7. Clear? Now you can say near about this one and this one is cancelled out. Clear? We are taking pi is what 3.14, this is the near about, we can cancel. So we can say this is 8 divided by 25. Clear? So 8 divided by 25 into 10 to the power 7. Clear to everyone? So from here we can say, if you write it, you can write like this, what is exact value you will get here. So if you solve it, okay, you can see here, actually this mass in gram, always keep in mind this is in gram, you have to first convert into kilogram. Clear? So here we will write 10 to the power minus 26. Clear to everyone? This value in gram, first we write this value in kilogram. Clear? So from here you can write like this, this is 26. Clear? And we can say this is what, 10 to the power 4. Clear? So from here we can say this is equal to what? This is 10 to the power 4. Clear? So 8 divided by 25, 8 divided by 25, this is equal to what? We can say near about, because we take here some approximation, but if you do here some exact calculation, you will find this value 0.58 into 10 to the power 3. Clear? Kilogram per meter cube. If you do here some exact calculation, you will find this answer. Clear? But it is given here that in a crystalline phase, density of sodium atom is given to you 970 kilogram per meter cube. Clear? So we can write like this, for crystalline phase density, we can write like this, 0.970 into 10 to the power 3 kilogram per meter cube. Clear? So now we can see density of a sodium atom and density of this crystalline phase of atom. Clear? Crystalline phase of sodium, we can say this density is having of same order. Same order means what? We can say here we are getting 10 to the power 3, this is also 10 to the power 3, this is 0.5 or this is 0.9. So we can say that density is almost equal. And why? Because we can say in sodium all the atoms, we can say they are actually closely packed. Closely packed means we can say that density of total crystalline phase, it is almost near about same to the density of sodium atom. Clear? So this is all about this question. Clear to everyone? Now student, we are going to discuss this question number 2.28, and in this question it is given to you the unit of length convenient on the nucleus scale is a Fermi, and 1 Fermi is given to you 10 to the power minus 15 meter. Okay. Nucleus size obey roughly the following empirical relation, R equal to R naught A to the power 1 by 3, where R naught is a value, this is equal to 1.2 Fermi. Clear? And A is what? This is mass number. It is given. Now what is our objective? Our objective in this question is to show that nuclear mass density is nearly constant. Clear? So how can we define nuclear mass density? How can we define here nuclear mass density? So we can say this is defined as mass of nucleus divided by volume of nucleus. Clear? Now how can we define mass of nucleus? Clear? Mass of nucleus is defined as mass number divided by Avogadro number. Mass number divided by Avogadro number. Clear? And it is multiplied with 4 by 3 pi r cube. Clear? 4 by 3 pi r cube, and we can say instead of r I will write this is r naught a to the power 1 by 3 whole cube. Clear to everyone? So from here we can see nuclear density. From here we can say nuclear density, this is given by A divided by Na multiply 4 by 3 pi multiply r naught cube multiply A. Clear? From here you can say A and A, this is cancelled out. So from here you can write like this is 3 divided by 4 pi Na, and this is R naught cube. Yes or no? So from here we can see this is a value of nuclear density. Now you can say that nuclear density is constant for different nuclei, because for different nuclei we are having different mass number, but value of 3 upon 4 pi is constant, Avogadro number is constant, and R naught value is constant. It means we can say nuclear density for different nuclei is same. It means because here we do not have any terms of mass number. Clear? So it means this statement is now proved. But actually we have to estimate the mass density of a sodium nucleus. Clear? So let's suppose if we are taking 1 kilomole of sodium atom. Clear? For an example, I am taking 1 kilomole of sodium atom. So in 1 mole we have Avogadro number, or we can say 6.023 into 10 to the power 23 atoms. 6.023 into 10 to the power 23 kilo atom. Clear? 23 kilo atom. So we can write like this, this is like this. Clear? So this is equal to 6.023 into 10 to the power 26 atoms. I am just assuming. Clear? 1 kilomole. Clear? So from here we can say this is value of mole or number of atoms that is present. So now we can put here all values. Clear? So we can write like this. Yes. So from here you can say we have this formula. This is equal to 3 divided by 4 pi Na, and this is R naught cube. Clear? So now from here we can write all values. This is equal to 3 divided by 4 into 3.14 divided by Avogadro number. We can say because we are talking about 1 kilomole, so 6.023 into 10 to the power 26 multiply. I can say this is R naught cube. R naught value is given 1.2 Fermi, and 1 Fermi equal to 10 to the power minus 15 meter. So 1.2 into 1.2 into 1.2 into 10 to the power minus 45. Clear? Now we have to solve it. Clear? So if you solve it, you will find this value near about 2.3 into 10 to the power minus 17 kilogram per meter cube. Clear? So this is a nuclear density of this sodium atom. Clear? This is nuclear density, or we can say nuclear density of sodium nucleus. Clear? Now if we compare this density with the density that we obtained in the previous question, at the time you will find this rho divided by rho Na, this is equal to what? 2.3 into 10 to the power minus 17 divided by 0.5, we obtained here this one 0.58. Clear? So 0.58 into 10 to the power minus 3, or we can say this is, yes, minus 3. Clear? So from here you can see we are getting this value. Actually this is positive because nuclear density always be positive, so this is positive. Clear? So we can see from here you can write like this, this is plus 10 to the power 3, so this is near about having order of 10 to the power 14. Clear? So from here we can say nuclear mass density is 10 to the power 14 times of mass density of sodium atom. Clear to you? So this is all about this question. Now dear student, we are going to discuss this question, and this question is 2.29. In this question it is given to you, a laser is a source of very intense, monochromatic and unidirectional beam of light. Fine. These properties of a laser light can be exploited to measure long distance. That is absolutely true. The distance of the moon from earth has been already determined very precisely using a laser as a source of light. Okay. A laser light beamed at a moon takes 2.56 seconds to return after reflection at moon surface. Clear? So I can write here total time taken by this light again reach to the initial position. This is 2.56 seconds. Let us try to understand given situation. Let's suppose I can say this is earth. Let's suppose this is earth, and let's suppose this is moon. Clear? Definitely you know this moon is actually revolving around earth because moon is a natural satellite of earth. Clear? Now we can say this is distance r, and this distance is known as lunar radius. Clear? Now let's suppose we actually targeted a laser light towards moon, and definitely that light will move with a speed of 3 into 10 to the power 8 meter per second. Clear? Now we have to find what is distance, what is the lunar radius. Now we can say this laser light first going earth to moon and again coming to earth after reflection. It means I can say total distance covered is 2r. Clear? So we can write like this, 2r, this is distance covered, and that is equal to c multiplied with time. Clear? Speed multiplied with time. So from here we can say r is given by 1 by 2 multiply c multiply t. Clear? So 1 by 2 into c. C is equal to what? 3 into 10 to the power 8 meter per second. And what about time? Time is given 2.56 second. Clear? So from here we can say this is 1.28. Clear? So we can write like this, value of r. Clear? Value of r, this is given by 3 into 1.28 into 10 to the power 8. Clear? So if we multiply it with 3 into 1.28, we can say this is 4, we have 2, so this is 8 and this is 3. Yes or no? Clear? 3.84 into 10 to the power 8 meter. Clear? So this is known as the lunar radius, and actually this is what? This is what? This is the distance between earth and the moon. Clear? Almost 3.8 lakh kilometer distance. Clear? So this is all about this question. Clear to everyone? Now dear student, we are going to discuss this question, question number 2.30. Clear? In this question it is given to you a sonar. Sonar means sound navigation and ranging, uses ultrasonic waves to detect and locate object underwater. Fine. In a submarine equipped with a sonar, the time delay between generation of a probe wave and reception of echo after reflection from an enemy submarine is found to be 77 seconds. Clear? So you can understand it like this. Let's suppose this is our submarine. Clear? Or we can say this is the generation. Yes. So let's suppose this is submarine. Let's suppose you can assume this is Indian submarine. Clear? Now let's suppose they are actually releasing a ultrasonic wave, and let's suppose here we have enemy submarine. Enemy. Clear? So definitely this ultrasonic wave is going and it is striking to this enemy submarine and again reaches to same point. So let's suppose total distance covered here as, so between total distance between submarine and Indian submarine, we can say between two submarines. Clear? And this is enemy submarine. So what is total distance covered? Total distance covered is equal to twice s, and this is equal to what? This is equal to speed of sound wave in water multiplied with time. Clear? So speed of sound wave, I can say this is 1450 multiplied with time t. Yes or no? So from here we can see twice s, this is given by 1450 multiplied with time. Time is given to you 77 second. Clear? So value of s, this is given by 725 multiply 77. Clear? So from here we can write like this, s is equal to what? 725 multiply 7. Clear? So I can say this is 7535, we have 3. So we can say this is 17, we have 1. This is 5075 multiply 5705. So 5, we can say this is 2, we have 1. So this is 855. Clear? So from here we can write like this, this is 55825 meter. Clear? So this is what? We can say this is distance between enemy submarine. This is distance between enemy submarine and the submarine from where you are actually releasing ultrasonic waves. Clear? So this is all about this question. Clear to everyone? Now dear student, we are going to discuss question number 2.31, and in this question it is given to you the farthest object in our universe. The farthest object in our universe discovered by modern astronomers are so distant that light emitted by them takes billions of years to reach the earth. Okay, fine. These objects known as quasars have many puzzling features which have not been satisfactorily explained. Fine. What is the distance in kilometer of a quasar from which light takes 3 billion years to reach us? Clear? So in this question it is given total time taken to reach this light again. So this is 3 billion years. Billion means we can say that is what, 10 to the power 9 years. Clear? Now can we convert this year into seconds? Yes. 3 into 10 to the power 9 into 365.25 multiply, I can say 60 multiply 60, now it is converted into seconds. Clear? Now our objective here is to calculate distance covered. So can we write here like this, distance is equal to, we can say, speed multiplied with time. Clear? And definitely we are taking the speed of light in vacuum, so this is equal to 3 into 10 to the power 8 multiply with time. So time we can say 3 into 10 to the power 9 into 365.25 into 60 into 60, and this is in second. Clear? So from here we can say this 3 multiply this one. Clear? So 3 multiply 3, this is 9 multiply 10 to the power 17 multiply 365.25 multiply 3600. Clear? And this distance we will find in meter. Clear? Now we have to just multiply it. So can we write like this, 365.25 and this is 10 minus 1 multiply 10 to the power 19 multiply 36. Clear? Now you can see, if you write this calculation, this is, let's suppose you can take this is 365. Now we are doing approximate calculation, 365 multiply 10. So I can say 3650 minus 365. Clear? And it is multiplying with 36 into 10 to the power 90. Clear to everyone? So from here we have just simple calculation, and from where we can find the total distance covered by light before coming to reaches us. Clear? So we can see, we can write like this, distance covered 3650 minus 365. 3650 minus 365, we can say 5 we have here, this is 4, so we can say that is 8, this is 5 2, so 3285. Clear? So 3285 multiply 36 into 10 to the power, we can say 16 kilometer, because this is 19 we can convert this into kilometer also. So first we will multiply 3285 36, 3285 with 36. Clear? We can say this is 30. Clear? 30. If we put here 3, so this is 48, I can say 51 5, 12 5 17, we have 1, 18 we can say this is 19. Clear? Multiply, we can say this is 15, we have 1. Clear? 25 we have 5, again we have 2, so this is 8 and this is 9. Clear? So 0, we can say 6, this is 12, we have 1, so 18 and we have 1, so 1 1 we can say 2, this is 11. Clear? So from here you can write like this, this is 11 8260 into 10 to the power 16 kilometer. Clear? Or you can also write like this, this is 11.8260 into 10 to the power 20 kilometer. Clear? So this is all about total distance covered by this light before reaching to our eyes again. Clear? So this is all about this question. Now dear student, we are going to discuss this question number 2.32, and in this question it is given to you, it is a well known fact that during a total solar eclipse the disk of the moon almost completely covers the disk of the sun. Clear? So now we can say this is disk C. Clear? C. Yes. So in this question it is given, it is a well known fact that during a solar eclipse the disk of the moon completely covers the disk of sun. Fine. From this fact and from this information, the sun's angular distance is measured to be 1920 second. Clear? It means you can say angle theta, or actually it is given here angle alpha. Angle alpha is given to you 1920 second. Clear? 1920 second. So can we convert this 1920 into radian? Yes. First we can convert this 19. Now if we multiply it with pi by 180, now it converted into radian. radian. So from here we can write like this, alpha into 6 by 180. Clear? So this is approximate diameter of moon. So whenever we are talking about condition of solar eclipse, at the time diameter of sun and diameter of moon is same, yes or no? When this when we can say moon almost completely covers disk, clear? So at that time you can find diameter, you have to find, so we know angle. This is the distance, or we can say diameter of moon, clear? Diameter of moon, it is given by angle. Angle is equal, we can say this is multiply 4.85 into 10 to the power minus 6 radian, clear? Multiply, clear? Multiply, we can say radius. So distance between earth and moon, it is given to you 3.84 10 to the power 8 meter, clear? So from here we can write like this, if you calculate it 90/20 into 4.8 3.84 into this is 100 and in meter, clear? So just calculate it, we are taking here approximate result 90/20, let's suppose I am taking it 5 and let's suppose I am taking this is 3.8, clear? And it is multiplied with 100, clear? So from here we can say this one is cancelled. Multiply 38 with 5, I can say this is equal to 0, we have 4, so 190 and multiplied with 100, clear? We can say this is 90 square, 19 square equal to what? This is 361, so near about 361,0000 meter, or you can see we can write like this, this is equal to 3.61 into 1 2 3 4 5 6 10 to the power 6 meter. So this is, we can say, approximate diameter of moon, clear? So like this we can calculate, clear? So this is all about this question. Now dear student, we are going to discuss this question number 2.33, and again this is a lengthy question and definitely informative question is too, clear? So now we are going to discuss, concentrate on a screen. A great physicist of this century, Dirac, loved playing with numerical values of fundamental constant of nature. Fine. This led him to an interesting observation. Dirac found from the basic constant of atomic physics, C means speed of light, E means charge of an electron, mass of proton, gravitational constant capital G, he could arrive at a number with the dimension of time, okay? Further, it was a very large number, its magnitude being close to present estimate on the age of universe 15 million years, okay, fine. From the table of fundamental constant in your NCERT book, try to see if you can construct this number or other, you can see, think of, okay, fine. If this coincidence with the age of universe were significant, what would this imply for the consistency of fundamental constant, clear? So definitely maximum information is given to you in this question, but there is no any other numerical value is given, clear? How can we start this question? This is very important. So actually it is given here that Dirac used some fundamental constant and he reached up to a conclusion that whatever the fundamental terms I am using, but its dimension, it is coming out to be dimension of time, clear? So actually if we use here hit and trial method directly, actually we also arrived this on this conclusion that a term tau means, we can say, time, it is given by E square over 4 pi epsilon naught whole square, clear? E square upon 4 pi epsilon naught whole square multiply 1 upon, I can say this is mass of proton, clear? Mass of proton, mass of electron square, we can see this is capital C cube, or we can say C cube. This is C cube and multiplied with capital G. Clear? By hit and trial method we find this expression. Clear? So from here can we find the dimension of this right hand side is equal to dimension of this tau? Yes or no? So first we can find dimension of this one. So actually we know f is given by 1 upon 4 pi epsilon naught, this is E square divided by R square. Clear? So from here can we find value of E square over 4 pi epsilon naught? Yes or no? So from here we can see this is equal to Fr square. We write this formula due to Coulomb's law of electrostate. Clear? So from here we can write dimension formula. Dimension formula of force, this is given by force. This is M1 L1 T minus 2 and this is equal to L2. So from here we can see this is equal to M1 L cube T minus 2. So this is dimension formula of this term. Clear? So we can write here this is equal to what? I can say, because we are writing here this is square. Clear? So this is equal to M2, I can say L6, and this is what T to the power minus 4. Clear? And it is divided by, in this question it is given mass of proton and mass of electron. So directly we can say this is M3. Clear? And this is C. Means C means what? Speed of light, LT minus 1. So this is L cube T minus 3. And what about dimension formula of gravitational constant? Clear? So gravitational constant, how can we find? Actually we know Newton's law of gravitation, F is given by G M1 M2 upon R square. Clear? So from here we can say dimension formula of capital G, this is given by Fr square divided by M1 M2. Clear? So value of F we can say this is M1 L1 T minus 2, we can say this is L2 and divided by, I can say that is M2. Clear? So from here we can say capital G, this is given by M minus 1 L3 and this is T minus 2. So this is dimension formula of gravitational constant. So we can write here this value, this is M minus 1, clear, L cube and this is T minus 2. Clear? So now from here we can write dimension formula. So from here you can say this is M minus 1 M cube, this is M2 and we can say this one is cancelled out. L cube L6, this one is also cancelled out. T to the power minus 4, here we have T to the power minus 5. Clear? It means we are getting dimension of time. It means this is exactly true. Clear? But this dimension analysis, it does not provide you an exact information that the formula that you written here that is perfectly true. Clear? So, but let's suppose if we put here all the values, then let us try to find answer. Clear? Now concentrate. Yes. So from here if we put here all the values, we can see now charge of an electron. Charge of an electron, we can see this is 1.6 into 10 to the power minus 19 into 1.6 into 10 to the power minus 19. Clear? 1 upon 4 pi epsilon naught. This is equal to 9 into 10 to the power 9 into 9 into 10 to the power 9. Clear? Now it is divided by, now we can say mass of a proton. Mass of a proton is equal to what? We can say 1.67 into 10 to the power minus 27 kg, and mass of an electron, this is equal to 9.1 into 10 to the power minus 31 into 9.1 into 10 to the power minus 31. Clear? Multiplied with, this is what? 3 into 10 to the power 8 meter per second. So we can write here this is 27 into 10 to the power 24. Clear? Multiplied. Now value of gravitational constant, this is given by 6.67 into 10 to the power minus 11. Now you have to simplify this relation. Now you can say sir itna simplify karna. Yes, yes, now we will simplify it. Clear? So from here you can write like this, 1.6 into 1.6 into 9 into 9. Clear? From here we can say 10 to the power 9, 10 to the power 9, this is 10 to the power 18. Yes, this is 10 to the power minus 1. Yes, and we can say 10 to the power minus 20, clear, divided by. From here you can see 1.67 into 9.1 into 9.1 into 27 into 6.67 multiply. 10 to the power minus 31 and this one minus 7 minus 18 minus 18 minus 39 and we can say this is minus 39 and we can say this is minus 27. So minus 39 and minus 27. So let's suppose we are assuming 40. So I can say 67, 66. So minus 66. So from here we can say this is 10 to the power minus 66. Clear? So now dear student, if you solve it, clear? If you solve it, you will find this value. I am just writing here. This is equal to 2.13. Clear? 2.13 into 10 to the power 16 second. Clear? We can convert this value into years also. So for the years you have to divide first with 365 into 60 into 60 into 24. Yes or no? So if you convert it, then you will find, I am directly writing here answer. So this answer you will find 0.667 into 10 to the power and we can say 9 years. Clear? Or you can say this is equal to 0.667 billion years. Clear? Now in this question it is given that age of a universe is near about 15 billion years. Clear? But by calculation we are getting this is near about 0.66 billion years. It means we can say value of dimensional constant also changes with time. Clear? So because age of universe is continuously increasing, it means we can say values of the dimensional constant is also changing with time. Clear? So this is just a roughly estimate and definitely we find directly this formula from different hit and trial method. So definitely a little bit lengthy one question, but yes, not a conceptual question. Yes, one important thing from this question you can see that yes, the time that we are getting is not same as the 15 billion years. It means time, we can say time of, or we can say values of the dimensional constant is continuously changing with time. Clear? So this is all about this question. So dear student, this is all about chapter number 2, units and measurement, NCERT and exercise solutions. So definitely you have enjoyed all the session and definitely you will find some key concept and you will find here exact solution of each question. Clear? So this is all about this session. Clear? Thank you so much.